Every day, billions of people reach for devices that shape modern life. Smartphones, laptops, electric cars. But few pause to consider the revolutionary invention that makes it all possible: the lithium-ion battery. You might think you know who invented it. After all, the 2019 Nobel Prize in Chemistry honored 3 scientists for its development. But the real story? It's far more complex. A tale of corporate competition, academic breakthroughs, and unsung heroes spanning 3 continents and 4 decades. The year is 1972. The Cold War is raging, and so is America's first major oil crisis. Gas prices are skyrocketing. Lines at pumps stretch for blocks, and the nation is desperate for energy alternatives. At Exxon's research lab in New Jersey, a British scientist named Stan Whittingham is working on something that seems completely unrelated to oil: superconductors. But sometimes, the greatest discoveries come from unexpected places. Whittingham, young and ambitious, had already earned a reputation as a brilliant materials scientist. His colleagues described him as meticulous, passionate, and unafraid to challenge conventional wisdom. In his lab, surrounded by the hum of equipment and the glow of monitoring screens, he noticed something peculiar. The material he was studying, titanium disulfide, had layers that could trap lithium ions between them, like a molecular sandwich. This wasn't just an interesting observation, it was the foundation of a revolution. What made this discovery so significant was its potential for reversibility. The ions could move back and forth between the layers, again and again. It was like discovering a molecular parking garage where atomic-sized vehicles could come and go at will. This was the birth of the first rechargeable lithium battery. But Whittingham's battery had a fatal flaw. It used pure lithium metal, which was incredibly reactive. So reactive, in fact, that his experimental batteries would occasionally burst into flames. Not exactly what you want in your pocket. The race was on to find a safer alternative, but progress seemed to hit a wall. The scientific community needed fresh eyes on the problem. Enter John Goodenough, a professor at Oxford University. The year is 1980, and at 57, many would say his best years were behind him. They couldn't have been more wrong. Goodenough's path to battery research was anything but typical. He had studied Latin and Greek in college before switching to physics, served in World War II as a meteorologist, and worked on early computer memory at MIT. This diverse background gave him a unique perspective on problem solving. Goodenough had a breakthrough insight. Instead of titanium disulfide, what if they used cobalt oxide? This simple change doubled the battery's voltage and made it far more stable. His team worked tirelessly, often late into the night, testing different combinations and configurations. The breakthrough came after months of careful experimentation, but the story of Goodenough's discovery has another layer, one that demonstrates the collaborative nature of scientific research. His key insights came partly from discussions with visiting scientists from Japan and Europe. One of these visitors would later play a crucial role in the next chapter of our story. Meanwhile, across the Pacific, in Japan, the pieces of the puzzle were slowly coming together. At Asahi Kasei, a chemist named Akira Yoshino was taking a different approach. Instead of using reactive lithium metal, he experimented with petroleum coke, a carbon material that could store lithium ions safely. Yoshino's journey to this discovery was fascinating. He had initially been working on polyacetylene, a completely different material, when he read about Goodenough's work with cobalt oxide. Yoshino's breakthrough came from an unlikely source: his knowledge of the petroleum industry. Petroleum coke was a byproduct of oil refining, considered little more than industrial waste, but in Yoshino's hands, it became the key to making lithium-ion batteries safe for commercial use. His team spent countless hours testing different carbons, running thousands of charge-discharge cycles, and perfecting the design. But here's where the story takes an unexpected turn. While these pioneers were making breakthrough discoveries, dozens of other researchers and engineers were making crucial contributions that history has largely forgotten. In labs across the globe, scientists were solving critical problems that would make commercial batteries possible. At Bell Labs, Ned Godshall and his team developed critical electrode materials that would improve battery life. In France, Jean-Marie Tarascon made key discoveries about battery chemistry that would lead to safer designs. And at Sony, a team led by Yoshio Nishi would finally transform all this scientific knowledge into a commercial product. The Sony breakthrough came from an unexpected direction. They had been working on video cameras and were desperate for a better power source. Their engineers took Yoshino's basic design and refined it for mass production, solving countless technical challenges along the way. In 1991, they released the first commercial lithium-ion battery. But calling it Sony's invention would be like calling the smartphone Apple's invention. The truth is far more fascinating. Think of it like a relay race, where each runner's contribution was essential. Whittingham discovered the basic principle. Good enough doubled its potential. Yoshino made it safe. And countless others added crucial pieces to the puzzle. Each breakthrough built on previous work. Each innovation solved a different piece of the complex challenge. But the race wasn't over. In fact, it was just beginning. The next chapter would be written in labs across the globe, as researchers worked to make batteries more powerful, safer, and cheaper. Companies like Panasonic, Samsung, and LG joined the race, each contributing their own innovations. Today, as we face climate change and the need for renewable energy storage, the battery revolution these pioneers started is more important than ever. Their invention isn't just powering our phones, it's helping to power a sustainable future. In gigafactories across the globe, massive machines churn out millions of batteries daily, each one a testament to human ingenuity and collaboration. And the innovation continues. In university labs and corporate research centers, scientists are pushing the boundaries of what's possible. Some are working on solid-state batteries that could charge in minutes and last for days. Others are exploring new materials like sodium and sulfur that could make batteries cheaper and more abundant. Companies like QuantumScape, Solid Power, and Form Energy are racing to create the next generation of energy storage. These modern innovators stand on the shoulders of giants, but they're not just following in their footsteps. They're blazing new trails. They're tackling challenges that Whittingham, Goodenough, and Yoshino could hardly have imagined. Batteries for flying cars, grid-scale energy storage, and even space exploration. So, who really invented the lithium-ion battery? The answer is both simple and complex. Like many great inventions, it wasn't the work of a lone genius, but rather a chain of discoveries, each building on what came before. It's a reminder that innovation is rarely a single eureka moment, but rather a journey of countless steps, taken by many different people. The next time you pick up your phone or drive an electric car, remember, you're holding more than just a battery. You're holding the culmination of thousands of experiments, hundreds of failures, and decades of persistence by scientists and engineers across the globe. You're holding proof that the biggest challenges can only be solved when we work together, across borders and across generations. Because sometimes the greatest inventions don't come from a single flash of brilliance, but from the combined light of many minds working across time and space to solve one of humanity's most pressing challenges. And as we face the challenges of tomorrow, from climate change to energy security, this lesson becomes more important than ever.